Hi, I'm Mike Smith with SAECO, and today we're going to be talking about some of the testing that we do from both a geotechnical laboratory standpoint as well as construction quality assurance and quality control testing. And with me today is Justin Thomas. He's a geotechnical engineer in our Tempe office. So let's kind of start talking about some of the tests that we do and why we do them. So, you know, with geotechnical engineering, we're trying to identify and evaluate characteristics of the on-site soils where a plan, building, bridge, roadway, you name it, might be going there. So as part of that process, we'll go to the site and we will drill into the materials below the surface, sometimes as shallow as 5 feet, sometimes as deep as 100 feet or more, depending on what how much data that we need to get. And then we'll be taking those samples into our laboratory to do testing on them. So the few that we're going to talk about is the plasticity index test, the Rvalue test, a Consol test, and a Swell test as well. And then we'll get into some other construction testing methods later. So Justin, why don't we start with, let's just talk about why, as a design engineer, the PI is such an important thing that we're trying to get a handle on during the geotechnical phase of the project.
Yeah, no, absolutely. So as a designer, one of the things that's really important is to know how much silt and or clay is in the material that you're building on. The components that make up the soil really define how that soil behaves. And so the PI it's an easy test that helps us to determine how much silt and or clay is in that material. And so then we can run that PI test and use the numbers that we get to basically determine how that material is going to behave. So basically what we do is we take that material into the lab and we kind of add a little bit of water to it, we roll it out, or we have another machine or another apparatus that we can kind of kind of use a little knocker on.
Just tamp it.
Yeah, tamp it. And that material behaves differently based upon how much clay is in there, how much water is in there. And so based upon that, we can determine exactly how much clay is in there or how much silt is in there. And so as a designer, long term, that's going to determine how much bearing capacity you're going to get, what the shear strength of that soil is going to be. And so it's just such a really easy test, really inexpensive test to do that it's kind of a no-brainer for you to kind of perform.
Yeah. Well, and it is easy, but we've seen when you try to get different technicians to come up with the same value, or looking at different companies doing that same test, it's very difficult to get the exact, and the method leaves you some room, some wiggle room there. You don't have to match up exactly. But how about the plastic limit and the liquid limit? Can you kind of explain why those are valuable in that test?
Right. So kind of as I mentioned before, the material changes its behavior based upon how much water is added and how much silt and clay is in the material. And so as you add more water to it, basically, and you roll it out or you tamp it, it's going to behave differently. And that's as it changes its behavior, basically from its plastic state to maybe a little bit more liquid state, you're hitting what's called a limit. And so that's where you get these plastic limits and liquid limits. And as you alluded to, there's kind of an art to it. So different technicians kind of have a little bit of a different feel for it, so to speak. So they might define the plastic limit a little bit differently than another technician who's rolling it out might have a little bit of a different feel for it. So that's why their numbers might just be just a little bit differently. And so that's why there is a little bit of an art to it. But yeah, so all that is just a phase or a state change between how that soil behaves.
Yeah, and I know I've always kind of had, at labs I've been responsible for, we don't just let anybody do that PI test, or it takes a little more patience. We want to make sure they can repeat the exact same thing every time they do it, because again, we're running that test on materials that are going to behave a little bit differently as we're running it. Now, the interesting thing about the plasticity index or PI test is that's something we use for both the design of the project and during construction, especially construction of a earthwork or an embankment kind of project where the structure, its long-term performance it really hinges on that PI result that we get. We also can run the test there's two primary preparation methods for the sample, right? There's a wet prep method and just kind of we'll call the dry prep method. Can you touch on kind of why we get different results when we prepare them that different way? And
so I mean, the dry prep method is kind of a quick and dirty method.
Yeah, because that's not really allowed by the procedure, but it's kind of the standard everybody
Correct,
uses, unless the specifications say you must use a wet prep.
Right. You see it more often in construction than you do in geotech, the dry prep method. And it's usually when you get into a situation where the contractor or some entity wants results within a certain amount of time. Maybe they want results within 24 hours, or they want results as fast as you can possibly get them. And so they're really pushing the testing lab to really kind of go to that dry prep method, and without really saying, hey, go to that dry prep method. And so that's when labs tend to do that. The wet prep method takes time. You're basically kind of conditioning the soil with a little bit of moisture. That's really all you're doing, is kind of getting it ready, making sure it has a little bit of moisture before you start the testing. And it's a much more uniform method, because when you're doing the dry prep method and then you start adding a little bit of moisture, you're not ensuring that all of the soil is evenly moisture conditioned. And so that's why you get a lot of variance. You get a lot of variability between tests. But if you adequately wet prep it, it's a lot more consistent in the long run.
Okay, good. Again, so that's a test that we both do during the design of a project and during construction. Another one of those tests is the sieve analysis. And the sieve analysis is essentially the range of particle sizes within a soil matrix. And during construction, it's pretty obvious what we use that for. But as it relates to the geotechnical aspect in the design phase, what is it that you're trying to identify in doing those sieve analysis tests during the design of the project?
Yeah, absolutely. So if you start with the end goal in mind, right, what we're looking for is a material that can really support the structure that you're going to be building on. And a sieve analysis basically gives us kind of a picture of all the different particle sizes that are in whatever sample that we've collected. And so when you just take a snapshot of the soil or whatever volume that you're looking at, how they kind of come together and how they compact, how they bear the structure on, it's really going to be dependent upon that kind of spectrum, different soil sizes. So if you, for example, just have one soil size, it's really uniform, then it's not going to compact very well. And so you're going to have issues during construction, and ultimately it's not going to potentially be able to support a structure very well. And so also, if you have a gradation curve that is actually really good, where you have some smaller samples, smaller sizes, some larger sizes, and it's really, really good, then you can actually have a soil that compacts really, really well. And so therefore, it becomes really easy to work with during construction, and compacts really well. And so that's one thing we're looking at.
Mm-hmm.
But also we get to see, for example, the percentage of material that passes the 200 screen. I mean, if you get 70, 80, 60% passing the 200 screen, that's a big red flag. That tells me that there's a lot of silt, a lot of clay, and that could potentially cause settlement or expansion issues down the line. And so we have to do further testing at that point.
Mm-hmm. Yeah, and when Justin mentions the 200 size or the 200 sieve, those are really small particle sizes, and we'll show you one of those screens with some of the video we get tomorrow. So on the some other geotechnical tests then, well, let's talk about, while the samples are being obtained and the logging takes place on the site when the drilling's going on, what other kind of data and observations are you focused on while we're getting those samples?
Yeah, so when we go out to a site, it's a holistic approach. We start by looking at the entire site, right? We want to know as much information as we can about that site as possible. And so really, before we even get to the first hole that we're looking at the entirety of the site. We're looking at the general topography, if there's any slopes. We want to know if there's any cuts or fills, if there's any existing development, because that's going to make a huge difference in our final recommendations. We also want to know if there's any undocumented fill, because we can't recommend an existing structure or a new structure be built on top of soil that was there from somebody dumped there, right? Because we have no idea how that soil was placed. And so there's a lot of information we can get just by taking a big picture look at the site, right? And so we go with this wide angle lens, and then we kind of narrow it down to the drilling. Mm-hmm. And so then once we get to the drilling, now we're looking at, okay, what type of soil is this? How does the soil feel? Is it gritty like a sand, or is it a little bit maybe perhaps softer? Maybe is the word perhaps not the right word to use, but softer might be something kind of like a clay. If you get it wet, how does it respond? That kind of gives you a little bit of idea how it's going to behave. And so then you start to classify this soil in the field, so you can kind of get an idea and start to prepare that log. And then you just take observations as the driller is drilling. What's coming out of that hole? Is there any construction debris? Is there any water? Do you hit groundwater? What's the moisture condition of the soil? These are all things you're looking at. Is there any caliche? Caliche is a common thing we hit here in Arizona. Not too bad. In some areas that we've drilled have been, like New Mexico and Las Vegas, Nevada, have been a lot worse caliche situations. But that stuff is really hard to drill through and really hard to excavate. Mm-hmm. So that's important for the contractor to know, and we put that into our report, the excavation conditions. And so these are all things that we're looking for. And so that's really the thing that we're doing. And then when we're actually taking these samples, we use a couple different samplers that we're using. And the drill rig actually has a 130-pound hammer on it that we can use to get some characteristics of the soil. And so we'll keep what's called blow counts. And the number of blows it takes, we've actually, the industry has actually correlated those to engineering, engineering characteristics of the soils that we can use to make recommendations for the designer.
Yeah. Okay. Good. And then We don't really have enough time to cover every single test that we can do as part of a geotechnical investigation, and it changes a lot depending on the kind of structure that is planned for a site. One thing that's unique to a roadway project is what's called an R-value test. And we don't do a ton of those, but perhaps you could touch on what that tells you as a designer when you get an R-value test.
Yeah, absolutely. So an R-value test is simply how does a soil respond to some type of bearing pressure. And it's something that kind of Caltrans out of California started to use a little bit more, and I think it was in the 1980s, and so it has started to become a little bit more popular. And it's really just a number to quantify how that material responds to a bearing pressure. And it's a number from 0 to 100. Obviously, the higher the number, the better that material is at supporting that bearing pressure. And that's really all it is. And so...
and we use that to determine or make a recommendation for exactly what the subgrade preparation, the roadway base, et cetera, for a road should be, given what the in situ materials are capable of bearing, right?
Right, exactly, yeah.
Okay. Then another test that we don't perform in-house, but it's still a pretty common one, are chlorides and sulfates. And as a designer, why do we do those, and who finds those valuable? What's the purpose of those tests?
Yeah, so those are typically done as a suite of corrosion testing, and those are really, really important because obviously we're going to be placing concrete, rebar, metal pipes, all types of material like that against this earth and against these soil materials that are going to be exposed to perhaps sulfates and chlorides, and so it's going to be important for them to know whether or not they're going to need to take any measures to kind of counteract those. So we also run pH and resistivity for that reason as well.
Yeah. And again, that's why it's so important for us to have as good of an understanding as possible as to what the use of the site is going to be. Because we wouldn't recommend running all these tests on every site because a lot of them just aren't needed. We're trying to provide the best value for what we do. And then also a couple of other tests that we'll be showing are the Swell and Consol tests. Maybe touch on the Consol test first, what that is used for.
Yeah. So consolidation test, it's a test where we take basically a sample of the material at a site, and we apply a load to it over time, and we kind of measure how that material responds to that varying load. And what we do is we increase that load over time, and usually it takes a couple of days, depending on how that material is responding. And there's two different ways we can run that. One is called a full cycle consolidation. Most of the time we don't run that. It's usually more for academic purposes, or if you absolutely need to know as much as you possibly can about the soil. And so there's a lot of information you can get from that. It's really accurate when you're trying to get settlement information, whether or not a material is over or under consolidated, or even some other more academic information about the soil. But so that's the full cycle consolidation. What's more common, especially here in the Southwest, is what's called a response to wetting. And what we do is we typically start to apply that load, and when you get to a point roughly about the anticipated bearing pressure, you add water. You saturate that material, and then you keep adding a little bit of load, and you kind of measure how that material responds to that water that you added. And so that can tell you if it's going to collapse or if it's going to potentially swell when you add that water.
Yeah. And then a lot of the tests that we've talked about are done on samples that have been, we'll call them disturbed or prepared in the laboratory, but the Consol test is actually done on an undisturbed sample, is that correct?
Correct.
So
yeah.
why do we do that?
Yeah, so we want to know exactly how the material is going to behave if it's undisturbed.
Okay.
Right? And so, yeah, so that's exactly why. One of the samplers that we used, it's called a ring sampler. It's about a 1 inch by 2 1/4 ring sample. And the material comes out essentially undisturbed. I mean, as undisturbed as you can get it, right? Yeah, and so you basically take that sample, prepare it, you trim it, and you put it straight into the test.
Yeah.
Yeah.
Okay. And then the Swell test then is a sample we do on a laboratory prepared specimen. So talk about why we do that one and how we vary the input characteristics to that test.
Yeah, so the Swell test, it's a little bit different than consolidation. And what you do is you kind of want to mimic the real world situation, right? The real world scenario. And so what you do is you prepare the specimen just as if it's going to be underneath, say, a slab or perhaps maybe a foundation. And you need to know what the laboratory proctor value is going to be, the maximum density, the optimum moisture of that material. So you can prepare that specimen. And then what you do is you apply a load. And that load is typically, for us, it's usually about 100 pounds per cubic foot, which is going to be about roughly what a slab is going to be, a slab on grade. And then you add water, and you see how it responds. You see, does it swell? Does it collapse a little bit? Usually it swells a little bit. You don't want that pressure to be so much that it doesn't do anything. So that's why it's lightly loaded. But yeah, so that's the purpose of that. You want to know if it's going to swell underneath a slab and crack your slab, basically.
Yeah. Good. Well, those are the ones I wanted to touch on. Are there any other lab tests that, on unique projects you might have been involved in, you want to add to that discussion?
Yeah, I think there's one.
Those are kind of the meat and potatoes of the geotechnical testing environment, but there's always that one-off you had to do.
Yeah, there's one that I think causes some confusion. It's very similar to the Swell test. It's called the EI, or the expansion index, and it's prepared kind of in a similar way. It's a test that it kind of measures the expansion of the swell, but it's consistent across the industry. So,
but it's after that volume change characteristic of those clays. It's just a different way to get there.
Right, exactly. And instead of, like, for example, the Swell test, we're allowed to kind of change some of the parameters to kind of mimic exactly what we're after. This test method, the expansion index, the ASTM test method basically tells us exactly what we can do. I mean, it tells us we have to do it at 144 pounds per cubic foot. It tells us exactly, how we are supposed to prepare that specimen. It tells us that we have to do it on all of the material passing the number 4. So there is no leeway in how we prepare that specimen or how we run that test. And then we compare the results basically against samples that have been run, using that method. And so that's why it's called an index test, right? It kind of gives us an idea of how this material is going to behave. And that's why a lot of agencies kind of specify using the expansion index test.
Yeah.
So, and it's not quite like a Swell test where you get a percentage. It's more of this has a potential to swell.
Okay. Good. Well, thank you, Justin, for taking a few minutes out of your day to explain some of these procedures to us. I hope that for the contractor's benefit there, that you have a little bit more of an understanding of what these tests mean. I'd also tell you that some of these tests, there's some regional aspects of these. Like when we talk about a swell and an EI test, Other parts of the country, they may run something different, but these engineering characteristics that we're trying to identify during the geotechnical phase of the project are done all over the world, all over the country.